Hi everybody, Sean O'Kane here. I'm here with Steve Schultz, President and CEO of SI2.
Yes.
We're here in Northern California for the 3D Architectures Conference, and you're just about to go in and
that's okay. I can give you 2 minutes.
Let's go. On a broader range of IoT.
Yes.
Now, some are calling the Internet of Things as in parallel to, and it's close to, the Industrial Revolution. The turn of the century is that big.
Yes.
You know, billions of devices that are connected, and with wearables, smart homes, smart cities, education,
biomedical,
healthcare, and infrastructure, and many, many, many more.
Yes.
So the question is, what is the path for adoption specific to 3D-IC?
Okay, great. Well, so the nature of IoT devices is that you have all this sensors, data collected automatically, and it has to be processed and communicated off chip, right?
Right.
So the sensors really are manufactured on different process technology than the memories, which is different than the microcontrollers and DSPs and such. So what we want to do is make the most efficient economic combination of that whole thing.
Okay.
And the way to do that is to use 3D technology to stack these die together, and it also will reduce the size and power consumption of these devices, which is essential for IoT.
Good point. Now, how is this going to change the design methodology?
Well, because design methodology is one that we're traditionally used to, the system on chip era, where everything is crammed into one single die. So this is going to mean that we now have to look at how do we optimize in a more broad sense across multiple die, across more diverse kinds of technologies. Security has to be a part of all this automated discovery and network configuration. And, of course, local software, remote software in the cloud and the fog. So this is really a change in methodology about how we think about an IoT product and how we think about what the silicon's role is in that product.
So what are the challenges, considerations, and standards that come into play?
Oh yeah, right. So there are gaps in the design flow. When you look at those methodology changes, we find that we're not completely prepared yet. There are some changes that we need, and we can get a job done, but it's painful, it's too costly. There's a lot of things we can do to provide communication of data of the intellectual property blocks in a standardized way. A lot better we can do on power to simulate and understand the power consumption. A lot more we can do with integrating the software role, and a lot in terms of just the physical part of taking a stack and integrating it for packaging and test, and maybe co-design of the package along with it. If you're going to have implanted biomedical devices, you're going to have a very tight form factor for that. And it'll probably have to use energy harvesting. You know, which is, I think, is really cool. But again, it all has to fit in a small space.
Excellent. Well said, well put.
So I got it right.
Oh yeah, I know. Once again, Steve Schultz, President and CEO of SI2.
All right, Sean.
Good luck on your presentation.
Appreciate it. Nice talking with you.
All right, take care.
When you change the paradigm, you create new markets. Let me repeat that. When you change the paradigm, you create new markets. Perhaps one of the best examples of this we've had in our lifetime has been the birth of the internet and the information revolution. Well, certainly that has been a key driver all the way back to the earliest days of DARPANET and research computers being connected. However, most of the world thinks about the internet and information revolution through the definition of the simple web browser. Sort of didn't create the internet, but it defined it. And that experience began a change in how we perceive, how we communicate with each other. And it has actually accelerated the pace of our entire society. So there's a lot to be said about paradigm changes and what they can do. Now, I remember the first time I actually had an experience with the very first Mosaic web browser which my team compiled for a Sun workstation. And we all gathered around the screen looking at it, and we were skeptics saying, no one will ever input their credit card numbers in something like this. But things do change because the forces are that compelling. When the economic forces are strong, things change. So the first wave is what we could call the fixed internet. Sure, this is the era of connected mainframes and servers, but also of PCs with Ethernet cards and cables 28K baud modems and AOL and download of BBS services and things like that. That was, in fact, an important critical enabler for us, and it changed the paradigm of how we communicated. It's not that it was entirely new, right? It built upon FTP and all kinds of other things, but we added some new protocols, but we changed the way we thought about it. That was the important difference. The second wave was the recognition that we wanted our information with us. We wanted to take it along with us. We're on the move. And as processing power improved and SoC integration enabled it, we had phones that were able to represent simplified web protocols. Remember WAP? Okay, and then we had the cellular connectivities went digital, and we had 2G, 3G, and 4G. Then tablets came along, and we have high-res displays and touch screens and Wi-Fi all the way up through AC and beyond. Well, this has basically been another means in which we had convenience and an instantaneous response of information from people to other people. But the third wave is the Internet of Things. And this is really a new information revolution of things. Not that they're getting up and revolting, but basically it is about a change in a paradigm. But this phrase was coined in 1999, I believe, and what we really see is it's about raw data that is automatically connected, that can create automated decisions, that can actually lead to a big vision, a bold vision, that automatically kind of optimizes and reconfigures our society around us. But the complexity is expanding. Let's kind of look back at that first wave. So we had some new software protocols, HTTP, IMAP, POP, things like that. That's great. But that was relatively simple. I'd say that the second wave, when we went mobile, was a pretty major event involving our silicon and semiconductor industry, because now we had to have integration of capability that was also portable and small, lower power. And we had to have these wireless chips that would drive in terms of base stations and routers and phones and tablets. And so this was an important wave, and we've been riding that, right? It's just beginning to saturate now. But the third wave is a lot more complex because it's a lot more diverse. And we have complex communication and security protocols that will be required. It's not going to be as simple as just thinking about the device. I know we're used to that. But we're going to have to think about the system, and I'll talk about that in a minute. The silicon will have more diverse content on it, and it won't necessarily all exist on a single die. And in the environment in which things are processed and communicated and optimized will be integrated and distributed, and yet very fragmented by market. So, it's coming, and it's big. Let's take a look at some of the numbers. Now, market research firm IDC has predicted that we are on track to have 28 billion new connected devices added to our internet over the next 5 years, by 2020. Now, just to put that in perspective, that is a greater than 900x increase from what we've had over the last 20 years to get to 3 billion. Think about that. Now, realize that the maximum number of connected devices with our version 4, IP version 4 protocol is 4.3. We're fast going to approach that limit, and we had better change pretty fast, right? Now let's look at the economics of it. Okay, so again from IDC, they're predicting that there will be a total of $7.1 trillion of technology, IoT technology in the market, with about $1 trillion already in place. So that's a growth of $6.1 trillion of opportunity. That's huge. These are unstoppable forces. Now, it would be tempting to consider that this is simply an incremental market thing that's going to happen alongside many other miscellaneous things. But I've come to believe that, in fact, despite all the hype and the fact that it's pegging about 9.0 on the buzzword meter, it hasn't even arrived yet, right? I mean, not really. So it really is, in fact, economically, it is driving many market changes and many paradigm changes. And because of that, it's an unstoppable force. And that will also give us a compelling event and an opportunity in the world of 3D ICs. So let's start with the definition. This is my definition. I say IoT is really all about connecting, that's emphasized, connecting things with information created by things to help decision-making, mostly by things. And hopefully, if we're lucky, to benefit humans. But the central point here is the connectivity, because if you take a look at the IoT system stack architecture from Goldman Sachs, it's pretty good here. And I know it's an eye chart, but you have your printouts. The lowest level of this is the networking infrastructure. That's the foundation. And the foundation of that, look at that, is security. And our security can't just exist in software. It's got to be in hardware as well. So we can no longer consider that a niche or an aftermarket thing. It's got to be integral to how we do design in IoT. Now, moving up the stack, you get to the connected things. And what you see is that there are about 4 categories here they've defined for the semiconductors and components range. You know, the communication part for communicating off chip, the processing power, the sensors, and microcontrollers and analog. But you notice that as you move upstream, you start to get to some vertically specialized modules and subsystems, because now you're getting closer to the markets, and we'll talk about the markets in a moment. And then finally, at the very top, you have the applications and services layer, and this is, if you will, getting closer to kind of the cloud, and, if you will. There's both horizontal and vertical views of this, and it will vary based upon, again, the market category that you're addressing. So let's take a look at some of the high-level technology characteristics of the system. It's a very diverse blend of technologies. Let's start with the network, right? The network architecture, you have a choice, right? You can have a point-to-point star or mesh architecture. Now, why would you care to think about that? You just wanted to have your little, smartwatch, whatever. Well, the thing is that you can't think about IoT without thinking about the system and the connectivity. It would be a mistake to ignore that. Because now you have to think about what is the nature of the data that's being communicated. Is it small packets that, when they're sent, always cause some event to happen? Or is it some continuous stream of data that has a very low information-to-noise ratio and has to be filtered out? Where do you want that processing to occur? Something on a little tiny battery or energy harvester, or do you want that to occur in the cloud? Or maybe it's better to occur at the edge. So there's a cost to everything. And as we look at IoT, we have to think about how we optimize. And again, security has to be central. At the devices, you have the silicon, of course, and a lot is involved in that. And there's the packaging and a lot of power concerns. And for some market areas like the wearables, there'll be a user interface and such. There's software running on this in most cases, right? You have your microcontrollers and such. So there's embedded software, but there's also server-side software. And this is like the cloud or the edge, and Cisco's calling that the fog. And you've got big data analytics doing all this kind of crunching to interpret the sensor-collected data, okay? There's a lot of opportunity, right? We've already got a whole lot of hype around big data analytics and sorting big data, but now, and you've probably been hearing about unstructured databases versus structured databases and such. So there's just a lot involved at the applications and services level. Now, diving into the silicon, let's take a look there. The IP content, of course, you've got to have sensors, a lot of MEMS kind of devices, and I won't list them all here. There's, I think I counted about 14 different types, and many of these products will require multiple sensors. And I think, as you know, it's not going to be where these sensors and MEMS devices are all created at 10 and 14 nanometer technology, right? They're optimal both in terms of reliability as well as in terms of cost. An economic point is way, way downstream. Then, of course, you have processors. Now, of course, you've got your ALUs and you've got your DSP architectures and GPUs and such. Of course, they have to execute software that's going to be contained in memories, but you also have the memory needed to capture data, handle configuration of security stuff and things like that. So you've got your embedded software. Your RF and analog, of course, you have to have that in order to get the information on and off chip. And then some devices won't have batteries. They'll actually use, let's say, heat or motion or vibration or things in order to harvest energy from the environment. And then in some cases, you're going to have markets that require custom packaging, or at least a very careful co-design and co-analysis of the package considerations, especially for tight form factors. So let's say that you've got a great idea for an IoT product. You might be a system integrator or an end user at IP House, or even a university professor, and you don't have a whole lot of money, but if you were to take all of these content pieces, the memory, the processor, the RF, let's say you got an imager, and then some new custom design work. Well, even if all of this IP exists as blocks, to create an SoC design that integrates all that verifies all that lays it out and routes it, does all that, is a lot of risk. And as we know, the NRE costs have been rising to do that. It adds risk, it adds cost, it adds time. What if we had a better way to do this, where we could actually take advantage of the economies of scale and have all of these pieces existing as reusable IP as die? They're already manufactured, you've got high volume, you've got cost effectiveness for each manufacturing process, and now you can stack them up and you focus on your new design content. That content now is where you have to focus your resources, and if you could stack that up and have that integrated in a 3D IC, you might be able to get to market faster, you might be able to prototype things faster, and then you have to look at what it takes to make all this happen. You need an environment. There's a lot of system simulation needs in terms of modeling and PDKs and the like. Well, what's the cost of doing an SoC design that has to worry about all of those details, a lot of it being redundant, versus the cost of a stack experiment that you might want to try out? So this gives you some opportunity to mitigate risk and, frankly, can enable a maker community for IoT designs. Now, when we talk about the wireless protocols, most analysts agree that Wi-Fi and cellular technologies will be probably dominant, right? Wi-Fi where it exists and cellular where Wi-Fi is not available. But there are some concerns. There's concerns over power, auto configuration, security, and the changes that are coming with IP version 6. Bluetooth 4.2 standard is coming out, and it actually features more reliable communications, lower power consumption, better security. But then again, there's near-field communications, and NFC is really good for some commodity products in the home, for example. I know I've heard about smart light bulbs that'll have NFC devices in them. But then you've got personal area networking devices competing, Zigbee and Z-Wave, and 6LoWPAN. By the way, 6LoWPAN is a personal area networking that is optimized for IP version 6 protocol. So think about that. So but we're not done. Look, Google Thread, they want to be the single networking standard in the home. And then you've got AllJoyn, which is a technology for IoT that's going to be providing automated device discovery and configuration. And then there's this accelerated innovation thing coming out of the MEMS industry group that's going to be providing some sensor I/O capabilities in terms of open source algorithms for sensors and interfaces for sensors. And finally, all of this has to be compatible with IP version 6. So that's quite a kitchen sink of IP content that you have to think about when you design your IoT silicon. Now, operationally, we've talked about the network discovery and configuration. In many cases, not all markets, but in many of these markets, you're going to have extreme low power design requirements, tight form factors in some of them. This example here shows a biomedical type of thing that could be implanted. And then, of course, security across the flow. And by the way, security consumes power, right? So everything that you do adds to the complexity of the problem. Now let's take a look at the market categories. So in the wearables market, we're all familiar with that. I had a Fitbit for a few months until I got tired of recharging it every 4 to 5 days. But there's smartwatches, Google Glass, and things like that. And I'll bet there'll be a million things tried. We'll have a gazillion things tried. Probably 80% of them won't stick and they'll fail. But there's a lot of volume and a lot of consumer opportunity there. Now, you look at biomedical. I'm personally very excited about the opportunities in biomedical because just think about how much information, if we could monitor a lot more real-time information about our bodies, and especially things either inside or attached, and then have that communicated to secure servers that can do the processing and the analytics and predictive things, we could lead to, I think, a number of medical breakthroughs. Unfortunately, while this would be a very high-margin business, I think it's going to take a long time to mature because of regulatory approvals and things like that. Now that you've got the industrial and B2B market, and of course we think about factory automation, there's a number of initiatives there. The German government has something called Industry 4.0, which is sort of the fourth generation of the Industrial Revolution. And it's all about smart networks, intelligent networks, connected supply chain analytics. And the U.S. has something called the Smart Manufacturing Leadership Coalition, which is doing an even broader attempt at collaboration there. So there's a lot of opportunity in industrial. Of course, connected cars. Automotive is one of our growth areas in semiconductors looking ahead. What with automated driver's assistance and then the connection with IoT devices, sensors inside and out, there's a lot of opportunity in automotive. Connected homes. Okay, so like wearables, I imagine we're going to see a lot of silly products. And I'm actually kind of fearing the day that my appliances start conspiring against me. And no, I'm serious. I was thinking, oh my gosh, I'm going to get this ransom email from my washing machine that tells me if I don't clean out my refrigerator, I may never eat or have clean clothes again. So you have to look at how are we going to manage the security of these things. Connected cities is a very distributed architecture and will require a lot of things, and there will be a question about who provides the information, who owns the information, and who pays for it, and who controls it. All right, now let's look at designing for IoT and what it takes and the kind of changes we see in design methodology. So this is just a big picture example, if you will, that kind of shows a lot of pieces. I know it's hard to read, but you've got things involving the traffic and network stuff, factory optimization, all this kind of stuff. But notice that they kind of put the cloud and the services at the center. Okay, so again, this is the system view. How do you optimize your silicon design for that? Well, let's look at this. In optimization, let's realize the semiconductors are only one part of this very diverse and distributed and fragmented, yet has to be integrated ecosystem. And so the more tightly integrated your variables are and your design variables and the trade-offs among these things, the more broad your optimization has to be in order to win in the marketplace. Because if you don't have the most efficient silicon choice to do whatever is going to be done in that system context, then your product won't win out in the market. Now here at the lower right corner, I've got a graphic that shows the kind of the, if you will, the trade-offs in designing a 3D ICs, and it kind of shows the supply chain segments between the foundry and IP and EDA and OSAT, but it also shows some of the design variables that you have to consider. What are the design variables for performance and profitability in a very distributed environment like that? So there's different kinds of integration needs. Since probably the late 90s, the term system on a chip has emerged as sort of a defining phrase that we equate with the term integration, right? So that means a single die that packs more and more transistors and more functionality. And that's worked pretty well for us. The problem is that, first off, scaling, traditional scaling, is approaching the economic limits in many of the market segments and many applications. And in fact, what we're seeing now is sort of a bifurcation in which there are the fewer companies, high volume though, that need the bleeding edge technology, but then a lot of the markets which have gotten off the train at 28 nanometers and are staying there, or at higher level process nodes. And so, we know that integration has to continue, and that the traditional interpretation of Moore's law is going to be seen as bifurcation. But in IoT, the needs for integration are more diverse. So these new integration requirements are going to force changes in our design methodology. So those new integration challenges, let's just realize that most of these IoT applications will need a variety of sensors. In most of the markets, low power is a concern. In fact, I would say it goes beyond just our traditional low power techniques, you know, voltage and frequency scaling and shut-off techniques, but really realize that a substantial part of the power consumption is in driving all of the IOs because you've got all of these connections. Well, what if you could find a way to reduce the number of IO drivers substantially? You could substantially reduce the power consumption for any given design. And realize that some of these devices will need more localized processing, some less, some will put more of it in the cloud or the edge, and of course some will have very tight form factors and concerns like that. Well, guess what? 3D ICs can address all these needs, but it's not the classic SoC anymore, because what's happened is you can't fit all of this on a single die. So I'd like to actually claim that maybe we're ushering in the beginning of a transition, or I should say an expansion of our mindset and our paradigm of what system on a chip is, and move from SoC to SOS, system on a stack. Let's take a look at the front-end estimation methodology that's used in coming up with new silicon products. And this is one I just kind of came up with quick. It's probably fairly representative of a lot of modern silicon SoC designs. But of course, you have to start with what the product requirements are. And you have your MRDs that says, okay, what are the features that are there? What standards does it have to comply with? You know, how long is the battery life, whatnot. And then you start saying, for that functionality, I do some first estimates of the software. That is a big job. That is a hard and difficult task. And there's many, many things that you can get wrong in this. But from that, you then say, okay, what's my memory configuration? What's that need to look like? What kind of bus architecture am I going to use for this? And you know, standard interfaces, power performance. So now you're defining the content and the constraints around the IC, but at a high level. Then you proceed to evaluate your manufacturing process options, the IP blocks that you can reuse from that, packaging options, estimate the new design effort. Then you roll all that up in terms of your cost and time to market, and you find out that it doesn't work. And so you have to go back and redefine it and iterate. And you do that until you run out of time. So let's summarize some of the uncertainties that we have in terms of design methodology. Include things such as you cannot assume a single die anymore. It's already, that's more complex. That's a lot more complex. You cannot assume a single process, manufacturing process. Extreme low power design techniques. And by the way, when you analyze your power requirements, you have to be thinking about optimizing in that system context. Software's got to be a part of it. Some of it will be local on your device. Some of it will be remote. You've got to figure out for your product design what's the most efficient way to distribute that processing task. More details with your IP blocks or IP die that gets exchanged. There's a lot of opportunity there for improved standards. And in fact, amongst SI2's member companies, we're hearing that quite a bit. Small form factor issues, as we've already discussed, and possibly the need for package co-design and co-verification and analysis. So, taking a look at the design flow in a little more detail, there are gaps. Well, guess what? There's always gaps. It's never stopped engineers before, right? We know how to live with the gaps. The cost, though, is in terms of the pain, time to market, the number of mistakes made, the wasted resources. So let's look at how we can do things a little more efficiently. So in a 2.5 or 3D design flow planning stage, the first thing is to plan the architecture, and you have your physical planning and package planning, and this kind of iterates. But very quickly, you realize that you have to think about IP that might be coming in. We just heard Phil talking about the memory products that are coming into the market here. And so when you're going to leverage that as part of a larger system, now you've got something that needs information so that as a part of your planning and your partitioning phase, and you're doing your pathfinding and analyzing your way through that, that you make smart choices. Then for any given die, that you've got the design process, which is going to have block level IP, third-party IP, or internal IP. And you need to figure out how to get that information into the automated flow. So you've got your PDK, hopefully understands about the 3D properties of TSVs and things like that. Electrical, physical, and thermal mechanical kinds of analysis as required. You've got chip finishing, extraction, DRC, LVS, mask creation, DFM, data prep, and finally, you can get it to the foundry. But that's just for one die. Now, you might be designing several layers in this. And so now you have to do that all over again. And guess what? It might not be the economic best choice to have the same process or even possibly the same foundry for that. And when that's all done, now you have to integrate that into the stack. And that would involve more information needed to do a smart job of packaging and test. Now, I don't have time to go over all the detailed opportunities for standards in this space, but I think that you can see that there's a wide range of opportunities available here. And I will just highlight a couple because there's been some progress in this over the last 18 months or so. And so we have standards now for chip-to-chip and chip-to-package description, for multi-die power networks, for thermal constraints and estimation, and a pathfinding spec will be coming out within some number of months here, in a couple of months, I assume. And in another project, there's a thing called a multi-level power model standard in work that will enable you to do power estimation and detailed calculations at either the block or even at the die level. So that is in the works as well. About 4 or 5 years ago, there was an industry alignment on standardization roadmaps. And Semitech and the 3D Enablement Center was working through this. And this slide is courtesy of Qualcomm, which was leading one of those roadmap efforts. And so they came up with the need for some design exchange formats. And out of that came up with kind of an identification of which kind of need would be championed by in which area, and then which standards body would be involved in that. And as you can see, SI2 had a fairly sizable role in this. And so in 2011, we formed something called the Open 3D Technical Advisory Board. And the charter of this group is to enable 2.5 and 3D design flows and solve some of those inefficiencies and barriers in terms of communicating the design data across the flow. And we actually have a very strong list of participating member companies, but we could always actively seek more help, and we would like to have more help as we do this. We want to make sure we're meeting the needs of the industry in that. And so, with that, I've talked about the third wave of our information revolution for things, and how it's a paradigm change and a huge economic and market opportunity, and that it really can be, if you will, a compelling event to help us make even faster progress, because I believe that 3D integrated circuits can help usher in an expanded view of our paradigm from SOC to SOS. Long live SOS. Thank you.